see who we got going on. Got at least one person. Hey, y'all. Happy Thursday. All right. Okay. I'm trying to open up my chat. I'll get attendance going next. So many things to get moving. All right. So let me do that. And I think that's what we need to get started. It's different doing this in my office than doing this in the classroom. I like being in the classroom. All right, so we got 2 more minutes and then we'll go ahead and get started. We've got 17 so far. All right, our number keeps climbing. So just make sure you're on mute if you're joining in. Yeah, all right. And you do not have to have your video on if you do not want to. It does not matter to me. Okay. We got 2 more minutes. Everybody's staying safe. At least you're not in the cold classroom today. You get to be in your nice warm home. Nothing to stay safe from yet. I know. You're glad I know. It's you need that like live interaction. I don't know what it is, but it helps. It helps me. Your class is like an icebox. It's not my class, it's the union. I don't have any control over it. I wish I could. I would crank up the heat. I would like that. But I agree, it is like an icebox. It is. So we got 1 more minute. The secret is to keep away on the desk. I could use a little space heater, you know, warm up my hands a little as we have class. That would be nice. And sit in the back, obviously. That's what I'll have to do next class. I'm just going to sit in the back. Oh, those hand warmers. Yes. Yes, that would be perfect. I used to, when I lived in Iowa, we would go to football games and I would have one for each hand and I would stick them in my boots so I would keep my my feet warm. Okay, so for those of you, that's a great thing, Madison. I'm glad you said that. For those of you who have physical clickers who cannot click in on attendance right now, write me something in the chat that says, hey, I'm here today, and then send me an email that says I checked in on the chat, and I will go in and I will physically change your attendance on iClicker, but I need you to put it in the chat and I need you to send me an email. So those 2 things for me, please, so that I make sure that you get credit for attending today. All right, and it would not be one of my classes if I did not start out with a joke, right? So I have a joke for you. It's not, I do have a joke for you today. I do. So it's not a traditional sort of joke, but it's a geeky joke, and I think y'all are really gonna like it. All right, so in October, the mitochondria turns into the mitochondria and becomes the haunted house of the cell. And y'all just get to listen to me laugh at the joke. But you know, like the powerhouse of the cell, it's really the haunted house of the cell. I love Halloween. It's one of my favorite holidays. So that one like pleased me on the science level and on the Halloween level. So I hope y'all enjoyed that. All right, so let's see. Now that we've got our joke done, I'll leave attendance open. So if you come in and you can check in, whatever it is, please go ahead and do that. Let's see. And then, oh, for attendance, sure, Bridget. So if you have a handheld clicker and you are unable to check in with iClicker right now, please check in on the chat, the Zoom chat, just like you did, but also send me an email that says, Dr. B, I was here today and checked in on the Zoom chat. Can you please fix my attendance? And I will go in and I will manually mark you as present for today. Okay. And if you have any problems, just let me know. Okay, so what you need today, we're going to work on the in-class problems, but what you also need is this chapter 6 activities. So glycosidic bonds and reducing sugars. If you have not downloaded these, you need to go and get them because we're going to work on them today. And then I want to point out that on chapter 7, if I could drag this, oh, come on. It's like everything's in one place over here. All right, chapter 7, I have the lecture slides up, I have the in-class problems up, and I'm gonna post videos very soon so that y'all can get started on those. I just had to complete some lab stuff because of the hurricane closures. So the answer, are we doing iClicker questions? We are not doing iClicker questions because it's not fair to those who have the handheld iClicker today or those people who had to evacuate or that kind of stuff. So I am not going to do iClicker questions today other than attendance. So that it's fair for everyone. So we'll have some more on Tuesday. We'll absolutely have some more on Tuesday. All right. Let's see, what are we doing now? All right, now I gotta switch over and, oh, I'm like, it's too much technology, too much technology. All right, here we go. So what we want to do, why does it do that? There it goes. my iPad like has memory. Okay, so we're gonna finish our in-class problems because we only have 2 sections, and then we're going to do those activities, and those activities are designed to target some areas where I think y'all still have some confusion, and so we're going to try and tackle those before the exam. Woohoo. All right, so polysaccharides, our 6th section is on polysaccharides. What's a polysaccharide? And please put as much as you can in the Zoom chat. So a polysaccharide, what is a polysaccharide? Polly tells us we have how many individual units? 10 or more, 10 or more, 10 to 10,000, yeah. So 3 to 9 is our oligos and poly is 10. So everything we talk about in this section and below is going to be greater than or equal to 10. So there are some polysaccharides that we need, loads, yes, that we need in order to function. So what we're gonna, oh, that's my kid's school. Okay. Sorry, y'all, that's my phone. I hope, let me see. Hello? Okay.
Our guidance from the Louisiana Department of Health guidelines classify multiple classrooms as a cluster and forest quarantining of the whole school.
Oh, hang on, y'all. I'm sorry.
And employees who have been on the campus of WS. Lafayette beginning Monday, October 5th, will quarantine for 14 days today. This quarantine will remain in effect until Friday, October 23rd.
Okay.
If your child has symptoms, consider contacting your healthcare provider and notify her if he or she tests positive. Because your child is quarantined, he or she should continue to complete assignments through Google Classroom. If he or she does not complete assignments and log attendance, your child
I'm sorry, y'all.
absent from school. If students become ill, they will be able to make up any missed work. Free COVID-19 testing will be available at Nichols State University from 8 a.m. to 6 p.m. October 12th to 16th, 2020, ages 5 and up. A deep cleaning of the school will begin immediately. Buses will run as scheduled. However, you may pick up your child from school between now and 3 p.m. If you wish, please visit your district.
Okay. Yeah. So they just called and said that the school is in quarantine. Yep. So can y'all hang on just a second while if anybody needs to make a quick phone call to take care of kids and that sort of thing, I totally understand. Y'all stay on. Give me just a minute. I'm going to stay on the Zoom, but I'm going to make a quick phone call. Y'all are so awesome. That's W.S. Lafargue. Yeah. Yeah. Hey. Yeah, I'm on a Zoom with my students, but WS called and they have they're calling it a cluster, an outbreak cluster. So they said we can go and pick up our kids anytime between now and 3 o'clock or get them at the end of the day. And then they're going to be on quarantine for 14 days. Okay. All right. I'm in class for the next hour and a half. Okay. Thank you. Bye. Okay. All right, y'all. Just a bump in the road. All right. So everybody okay? I'm going to record this. I'm going to post it. No big deal. So if you need to go, I'll post it. No big deal. I understand. All right. So similarities and differences in the following polysaccharides: amylose and amylopectin. What do we got in amylose and amylopectin? What are these two things found in? They're both what? They're both D-glucose. They're both D-glucose units. That's true. That's true. They're both found in plants. Okay, what else? Good, plants, yes. In plants, what do we call them together? They're not both structural. What do we call them together? We call them, it was a good try. We call them starch. So amylose and amylopectin together are starch. And so what's the function of starch? If it's not structural, it must be storage. Good, storage. That's our function, right? Because plants, it's okay. So plants can't make their own food 24/7 because the sun doesn't shine 24/7. So when it gets dark, their food source has to be something that they made during the light and then stored it. And so that's what starch is. Starch is their storage molecule. And together inside of starch, we have amylose and amylopectin. There's another similarity. And it has to do with how the glucose units are connected. Anybody know?
Is it something about the coil?
It's not about the coil, but it is about units linked with alpha. That's supposed to be an alpha. That is not an alpha. Alpha 1,4 bonds. Alpha 1,4 bonds, glycosidic bonds. Okay. So those are all of our similarities. You could also say that they're also polysaccharides. They're all polysaccharides. Right, that would be another similarity. How are they different though? Anybody know? Amylose versus amylopectin. Ah, branching. So amylose is a straight chain. And we call it a straight chain because it goes one after another, after another, after another. But y'all are right that amylose is going to coil. So just like your phone cord, right? Your old time phone cord, I actually have one in my office, right? Even though it's a straight chain, it's one cord, it actually coils on itself. So straight chain that coils, yes. And then our amylopectin is different. Our amylopectin has branching. And how does it branch? Anybody remember how it branches? Is it an alpha 1,4? No, it is a 1,6 alpha or beta. That one's going to be an alpha, right? You can't have exactly the same bond in a branch. It's going to be different. But they are both alpha. Okay. So that's A. That's A. So let's do B. Now we're going to talk about amylopectin and glycogen. How are those two similar? So we could do this. B. Both what? Both are polysaccharides if they're in this unit, right? Okay, but now we're talking about amylopectin and glycogen. How about their function? Do they have similar functions? Yes, they do. What is that similar function? They're both used in storage. So they are both used in storage. So this leads us into one of the differences, right? So if we have amylopectin and glycogen, we know they're both used in storage, but amylopectin is storage in what kind of a organism? So this is plants, so just like we said before, but you're right, Hayden, it is glycogen. It is glycogen. It's found in animals. I'm sorry, y'all. Animals. That is correct. What else? There are some other similarities. They're both D-glucose again. They both branch. Their branches are the same. Their branches are 1,6, alpha 1,6, and their chain, right, is also an alpha 1,4. Ah, but very nice, very nice. So amylopectin branches every 25 glucose units, whereas glycogen branches every 12 glucose units. Good catch. Okay. And that's all the ones that I know. So I think we're good. Okay. So let's try another one. Let's try amylose and cellulose. How are these similar? I'll give you the giveaway one, right? This is like the middle square on bingo. They're both polysaccharides. What else is similar? Cellulose don't coil. They're both straight chains. Okay, so they're both straight chains. Okay, what else? Cellulose doesn't coil, but they're both straight chains. That's true. So let's start some differences. Amylose and cellulose. C-L-U-L-O-S-E, right? So our cellulose does not coil, and amylose will coil, right? It's like having a straight cord and having a coiled phone cord, right? They're both straight chains, but they behave differently, right? Okay, so beta, so cellulose is beta. Cellulose has beta 1,4 linkages. That's right, beta 1,4. How about amylose? What did we say that was? Alpha 1,4. That's true, that's true. What else? What's the function of amylose? We already said this, but it is a difference. Used in digestive, it's cellulose. Amylose is storage. Amylose is storage in plants, right? Whereas cellulose is structural. A-R-U-C, structural in plants. Good. Good. So one of them we can actually use. So amylose, we can eat it and we can get energy from it. Cellulose we cannot break down. The cellulose, because they don't coil, right? They can lay one right on top of the other, on top of the other, on top of the other. And so it ends up being very, very, very strong. And so we actually have a really hard time breaking that down in our digestive system. So it's actually good to eat it. It actually does help our digestive system run properly, but we actually can't break it down for energy purposes, right? So good. Okay, and let's see, I'm trying to think if there's anything else. Oh yeah, they're both D-glucose, right? They're both D-glucose units. Anybody else think of anything else? I think that covers it. Okay, so now we got to do B. So B, cellulose and chitin, both I think that's for the last one. Yeah. Okay, so what can we say about cellulose and chitin? They're both what? So they're both structural. They're structural in different organisms. So let's talk about what those different organisms are. Cellulose and chitin. Cellulose is in what organism? Plants. And chitin insects, right? And those exoskeleton, right? And those really, really hard, hard things. Good. Let's see. So they're both structural. They both, y'all said beta 1,4 linkage. What else did y'all say? I think that was it from that one. They're both unbranched. And I think that's it for similarities. There's something else that's different about cellulose versus chitin. Chitin's kind of a weird one. Anybody know why chitin's weird? We said cellulose has glucose units, right? Does chitin have glucose units? Ah, it's the amide group. Good, 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 good. Okay, so when we have glucose, right, we normally have this ring, right? And then we have it participating in a glycosidic bond with another ring. And you have hydroxyls and you have hydrogen and you have your CH2OH, right? CH2OH. And you'll have hydroxyl, right? This is all stuff we've normally seen. But what's really weird about chitin is that chitin has an amide group, which is a nitrogen. Let me see if I can scooch this stuff over. There we go. Which is a nitrogen. So you have a nitrogen bound to a hydrogen, and then that nitrogen is bound to a carbonyl group, and then the carbonyl group is bound to a methyl group. And so when we see this together, a carbonyl with a methyl, we call this an acetyl group. Okay, whoa, A-C-T-Y-L, acetyl group. And then we call this nitrogen an amide group. So that's why they call it N-acetyl, E-T-Y, N-acetyl glucose, G-L-U-C-O, glucosamine, amen, A-I-M-I-N-E, glucosamine, N-acetyl glucosamine. And so that's where the name comes from, because you had glucose, you have an amide group, and you have an acetyl group. So I know it looks like a really long name, but they actually did name it pretty well. They actually did name it accurately. All right. Give the name of one or more polysaccharides that matches each of the following descriptions. Not digestible by humans. We talked about this a little bit, right? What's not digestible by humans? Aha, cellulose. There's another one. What's another really strong one? But it's not in plants, it's in insects. Chitin. Chitin, yes. All right, let's see. Storage form of carbohydrates in plants. So generally we call it starch, but what is starch composed of? It's composed of two things. Amylose and what else? Amylopectin, A-M-Y-L-O. Y'all, I can't spell today. Okay, C, contains only alpha-1,4 glycosidic bonds. Only alpha-1,4. Amylose. I want to like skip the first letter. I don't know why. Amylose. Okay, glucose polysaccharide with the most branching. There's only two with branching. Tell me the two with branching. Glycogen is one, and amylopectin. Tell me about the branching patterns of the two. Glycogen branches every 25, not 25. Glycogen branches every 12. Amylopectin branches every 25. So which one has the most branching? That one is going to be glycogen because it branches more frequently than amylopectin. Yep. And y'all don't worry about spelling. If we worried about spelling, we'd be here all day. We're not going to worry about that. All right, so give the name of one or more polysaccharide that matches the description. Storage form of carbohydrates in animals. This one, maybe, is that from a previous one? Glycogen. We store glycogen in our liver. So we do that. Contains only beta-1,4 glycosidic bonds. So this is a non-branching. And beta-1,4, when you see that beta, I want you to think something really strong, right? Cellulose. What else has beta-1,4 glycosidic bonds? Chitin. Good. Okay, let's see. Contains both alpha-1,4 and alpha-1,6 glycosidic bonds. Amylopectin. What else? Glycogen. All they differ in is how often they branch. They're basically the same thing. They just differ in how often they branch. Produces maltose during digestion. So that indicates that this is something we can digest. So you shouldn't say chitin and you shouldn't say cellulose. So glycogen. And what's made just like glycogen? There's another one that's just like glycogen, except it branches at a different frequency. Right? Okay. All right. So those you kind of have to study. You just kind of have to memorize some of those, right? I'm sorry. Bad news. All right. Explain whether the following, we're going to have to make flashcards would be a good, flashcards would be a good idea. You know what's a fun, I don't know if that you really call it fun, but if you do these, I don't remember, Venn diagrams, right? And you can do the different sugars and see what things are in common between the two and what are different. That's kind of a good thing too. Yeah, but if anybody makes flashcards and they want me to share it with the class, I'm happy to do that. I'm absolutely happy to do that. Okay, so explain whether the following blood types can be donated to a person with type B blood. In order to understand our blood types, all you have to know are the sugars that are on the outside of your red blood cells. So all of your red blood cells have they're like little sugars that are just sticking out from it, right? Is there somewhere in the book I can find it? Yeah, they're in section 6.6. Okay, so on your red blood cell, you have these little sugars that are sticking out. And the sugars are in a chain. So you have 1, 2, 3 sugars at least in every chain that sits on the outside of your red blood cells. And the reason that you have these things sticking out of your red blood cells is that so that your body can tell something that is you versus something that is foreign, right? If it's my cells, I want my immune system to look at that and say, hey, it can stay. But if it's foreign, I want my immune system to recognize it, mark it for death, and kill it and get rid of it, right? Because usually that gets rid of our viruses, our bacteria, anything foreign that enters our body that shouldn't be there, your immune system is supposed to take care of it. And so basically what you have to remember is that you'll reject anything that doesn't look like you. So if you're a type O, if you have type O blood, that means that you have a sugar chain that has these 3 things on it: an N-acetylglucosamine, a galactose, and a fructose. If you're type A, you have that same 3 chain, but then coming off of that second sugar is an N-acetylglucosamine. So your N-acetylglucosamine marks it as something different. Same thing with a type B. If you're type B, you have that same 3, and then you have an extra one. But in this case, your extra one is a galactose. All right, so you can receive blood from anybody that is just like you. So type O can receive from type O, and you can receive anything that is less than you. So if, for example, you are type A can receive blood from type O, right? How do we know that? Well, type A has these 4 things attached to it, right? Well, it can receive anything that is like it or less. So if we look at type O, what we see is type O is just 1 less. So it doesn't have this N-acetylglucosamine, but the rest of it is just like type A. So type A blood can receive type O blood. Okay, so that's what you kind of have to keep in mind when you're thinking about these blood type problems. So let's answer what the book asked you. Explain whether the following blood types could be donated to a person with type B blood. Okay, so if you are type A, donated to a person with type B. So we want, I'm not writing. Okay, type B blood donated to who? So we are type A and we want to give to type B. Can we do that? What do y'all think? No, 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 don't do it, don't do it. You will possibly kill your patient. Why? Because the type A blood, right, has this N-acetylglucosamine group on it. And the person is type B. They don't have N-acetylglucosamine. So their immune system is going to look at that N-acetylglucosamine and go, not happening, not in my bloodstream. And so it's going to basically start coagulating the blood, clotting the blood. And that can be a systemic reaction and you could kill somebody that way. So blood type's important. Okay, how about AB? Can we give AB blood to someone who is type B? Got to think about this one. No, you cannot. You cannot, because someone who is type AB, if you have a red blood cell that's AB, you have the A chain and you have the B chain. The person who's a type B blood only has B, right? So if you gave blood this way, if you gave AB blood to someone who's B, the B person would look at this A antigen and go, nope, that's not right. And it would start to coagulate the blood and you would kill the patient. So the answer to that is no. But you could go the other way around. You could go the other way around. So what if you had B blood and you were trying to give to AB? Could you do that? Yeah, then this is a yes. This is a yes. You can do that. Because an AB person has B antigens, B, sugar molecules, and so does the B person. So it's fine. That's fine. Yeah, so let's talk about real quick type O and type AB. So type O, whoa, here we go. Type O, what do we call someone who is type O? Universal donor, right? They can give blood to anyone. Why? Because everybody's got those three. So no one would reject type O blood. That's why when you watch medical TV dramas, guilty pleasure, I'll admit it, they'll wheel them into the ER and they'll go, hang a bag of O neg and type and cross, right? So what are they talking about? They're saying if they need blood, you're going to give them O negative blood. It's really O negative, but we're not talking about the RH factor in this class. We're only talking about the types. The RH factor is a little bit different, but that's what gives you the plus and minus. So they're going to give O negative blood so that it doesn't matter what blood type they are, they're not going to reject the blood. And so that's why if you are a type O, whether you're O negative or O positive, if you're type O, please, 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 please give blood. Please give blood. How about type AB? What do we call someone who is type AB? Anybody know? Yes, universal recipient. IPENT, recipient. So that means that they can get blood from anybody because they have all of the sugar chains. They won't reject anything. Yeah. Okay, so let's try this again. Let's try again. Let's see if we can not kill somebody this time. Explain whether the following blood types could donate to a person with type O blood. If we've got B and we're trying to go to O, can we do this? So B, give to someone who is O. Absolutely not. Oh, y'all are awesome. Can't do it. Absolutely not. Okay, B, what if we want to give from AB to O? No, no, don't do it. Don't do it. Please don't do it. You can't give anything other than O to O. So this is the drawback of being a type O. You can give to everyone, but you may only receive type O blood. So that's why it's like doubly important if you're a type O person to give blood, because that's the only blood that you can receive. So give blood, give blood, give blood. All right. How's heparin different from glucose polysaccharide? So before we answer 6.49, let's answer 6.50. Why do we need heparin? Like, what's the job of heparin? Prevent clotting. Good. Prevent. We call this an and I'm going to, Jacques, I want to talk about this. This is an anti-coagulant, A-G-U-L, coagulant. Now, you've probably heard on, like, I don't know, commercials, whatever, like the Bayer commercials, they'll say, you know, take aspirin, a low dose aspirin, if you're prone to heart disease, because it's a blood thinner. It can't actually thin your blood. That's actually a lie. It's hard for people to understand some scientific words like anti-coagulant. That's kind of complicated, right? But it prevents clotting. It's the same thing. But the colloquial term is blood thinner, but nothing's going to thin your blood. It's going to prevent clotting. And so the heparin is actually, whereas glucose, right? A glucose polysaccharide is many, so a glucose polysaccharide is many glucose monomers, right? But a heparin polysaccharide is many disaccharide units. So it's those disaccharide units, and those disaccharide units are really kind of weird because they carry a charge. They are charged, they're negative. And so that disaccharide repeats over and over and over again in the chain. And because it's charged, it prevents clotting from happening. Okay. So we good on that? Y'all ready to switch over? Yes. All right, so go to Moodle and get your little activity. We're gonna start with this one, activity 22, the glycosidic bonds. So I'll give y'all just a second to go ahead and pull that up. Okay, so I'm hoping y'all are with me, right? Okay, so when we talk about making chains, right, we have to form what's called our glycosidic bond. And our glycosidic bond is going to be able to take us from one monomer, we're going to link them together, and now we're going to have a disaccharide, right? So this is how we make chains. So if we have an overall general reaction, so here's our molecules, right? Where we're going to call this, it's a weird thing, we're going to call this R. And that R is bound to a hydroxyl group. And we're going to add another molecule, and that molecule we're going to also call R, and it's bound to a hydroxyl group. And when it undergoes this reaction, you're now going to form a new molecule, right? And it's going to be an oxygen in between. But what happened? Well, we took a hydrogen from one molecule and we took a hydroxyl from another molecule and we pulled them together and we made what?
Water.
We made water. Woohoo, we made water. Okay, so what kind of a reaction has that overall mechanism? Condensation. This is a condensation. So in condensation, if you put your glass of water out on the table, what's going to form? Water. So water is going to be a product in a condensation reaction. Hydrolysis is going to be the opposite, and we'll talk about that in a second. So don't forget that. But this might be something nice to write on, like, your scratch sheet of paper. You show it to your camera for the exam, right? And then as soon as you put it down, you can write whatever you want on it. So if you write this overall reaction that I drew out, you're going to be able to easily recognize things. So this might be a good thing to do. All right, so we're going to answer some questions about this reaction. In figure 1, are the glucose molecules that are reacting shown as the alpha or the beta enantiomer? I want to say enantiomer, but that's not right. It's the enantiomer. So are we beta or are we alpha? Okay, alpha. So how did you know it was alpha? Y'all are right, alpha. We have to go up here. I'm going to erase this stuff so that I have some room. Okay. So we have this, whoa. We have this carbon 6. This always sticks out of the top of the molecule, right? And then what are we looking at in order to determine if this is alpha or not? We're looking at the hydroxyl. So y'all are so on the ball today. It is trans because they're opposite, and not tans, trans. And that would tell you that it is alpha. Very good, very good. All right, so now let's see. Which carbons are bonded? Oh, but let's do our other one too. Let's double check our other one. I forgot. So we have, here's our one that goes out the top. And what hydroxyl are we looking at? Are we looking at the one that's highlighted here, or are we looking at the one that's on carbon 1? We should be looking at the one that's on carbon 1. Good, carbon 1. Good. So we see that that's also trans and alpha. Okay, so they're both alpha. So which carbons are bonded in the glycosidic bond in D-maltose? So that's our product. So I want to know what carbons are bonded. So let's kind of zoom in so that we get a nice idea. All right, so if we want to know which carbons participate, we have to number them. How do we know where to start our numbering? We find our anomeric carbon. So here we're bound to one oxygen, here we're bound to another oxygen, okay? And so there's no other carbon bound to this anomeric carbon. So we call that carbon 1. If we had a CH2OH, something like that, this would be 1 and the anomeric carbon would become 2. So that's the other thing you might see. So you have to be very careful of that. But there's no carbon attached here, so we're going to call it carbon 1. And I could go around and number them all. Like I could go 2, 3, 4, 5, 6, but we only really need the 1. All right, so this was in A. How about in B? Where's our anomeric carbon? Right here. Bound to 1, 2 oxygens. Good. So now we're going to name it. I'm going to go 1, 2, 3, 4, 5, 6. So tell me which carbons are participating in the glycosidic bond. One and four. So carbon 1 and carbon 4 are participating in the glycosidic bond. So technically, now you have to be very careful about this. This bond right here is the only one that's actually a glycosidic bond. Because if you come over here and look, this one, let me highlight it in green. This here, you already had an oxygen there. So where are you actually forming a bond between a carbon and an oxygen is right here. So the anomeric carbon is the one that's going to lose the hydroxyl group and is going to bond to the oxygen. And so it's really important that you know that that's the glycosidic bond. It's not two bonds, it's only one bond, and it's the one between the anomeric carbon and the oxygen. So be very careful about that. Does that make sense? It's really hard that I can't see y'all. Okay, so if we come down, right, carbon number linked on the left glucose molecule was carbon 1, and carbon linked on the right was carbon number 4. Good. So then number 3 is, do you see why the glycosidic bond in maltose is called an alpha 1,4 bond? And it's because it's in the alpha orientation, and it's between carbon 1 of one molecule and carbon 4 of the other molecule. But which one of these two carbons is actually participating in the glycosidic bond? Only carbon on the left glucose is participating in the glycosidic bond. Only this one. Only one in the glycosidic bond. Okay. All right, so let's go on. All right, so we just did D-maltose, so we just did this one. Hang on, I'm sorry, y'all. Hey. Can you put him on? Charles. All right, Charles, you need to go change right now. Our mom's gonna come home with a garbage bag and start throwing away toys. Now. Okay, thank you. Please do. Bye. Sorry, y'all. All right, so I cannot believe I'm going to post this recording to YouTube. I find that hilarious. Okay. Let's look at our question. Determine the glycosidic bond in D-lactose. Everybody has used that. That's the trump card. I'm going to go in your room and I'm going to take a garbage bag and it's all going. That's the trump card. Y'all are so sweet and so understanding. I really appreciate it. Let's see. Okay, so the glycosidic bond in D-lactose. So what are we going to call this? I want y'all to try, and once you get it, put it in the chat. Good. So look, y'all are getting some answers. Good, good, good. Beta 1,4. Y'all are right. Right on. Y'all are rocking it. Okay, so how did we get that? Let's make sure we understand how we got that. Here's our anomeric carbon. So that's carbon 1. here's our anomeric carbons. That's 1, 2, 3, 4. So that's where our 1 and our 4 come from. And then beta, because this is top, and this glycosidic bond right here is also top. And so cis is the same thing as beta. Okay. All right, now, what's our next one? The glycosidic bond, oh, and D-sucrose. All right, so let's look at D-sucrose. What do you notice about the name of the glycosidic bond in D-sucrose? There's something different. It's got 2 letters. Why does it have 2 letters? Yeah, the alpha and beta. Oh, Jason, that's exactly right. Both anomeric carbons are participating in a glycosidic bond. So there are actually 2 glycosidic bonds here. There are 2. And that's why you have an alpha beta designation. So if I count this, right, that's 1. All right, now be careful. Look at your sucrose. Why is this carbon that's participating in the glycosidic bond carbon 2 and not carbon 1? Right? This is our anomeric carbon, so why isn't that carbon 1? There's a carbon on the outside. So this carbon that's actually outside of the ring that's bonded to the anomeric carbon is carbon 1. So this one gets that designation of 1, while my anomeric gets the designation of 2. Yeah, that's a tricky one. That's a tricky one. So this is why your alpha beta, you have 2, well, I don't know how I want to say that. You have alpha and beta because you have 2 anomeric carbons participating in glycosidic bonds. Come on. Oh, like my screen has frozen. Come on, don't do this. Fingers crossed. See, and that's really weird. And it all moved down. Did y'all see that? It all moved down. That's so weird. Okay, right? Because you have 2 anomeric carbons participating in glycosidic bonds. And if I could move this stuff back up, right? It was there. Okay, today is not my day. Today is totally not my day. That's okay though, it's okay. All right, so look at number 5. The glycosidic bond in D-sucrose is different than most designations because both anomeric carbons, right, are participating in that glycosidic bond. That's all it is, that you have 2 in there. So it says now label the monosaccharides in sucrose as alpha D-glucose and beta D-fructose. So which one is which? So we'll call them A and B. What is A? Is A alpha D-glucose or is it beta D-glucose? So this one right here. This one is our alpha D-glucose and this one is our beta D-glucose. Because all we have to do is we have to look at this CH2OH group here and look at our glycosidic bond and say they're trans. So that's alpha. But if I look at my second molecule, I say, okay, it's on the top and this one's also on the top. Those are my 2 glycosidic bonds. This is why it's really, really important. Why did you name them glucose and not sucrose? Because sucrose is a disaccharide. And the sucrose disaccharide is composed of 2 glucose monosaccharides. Okay, So make sure you can identify those glycosidic bonds. That's really, really going to help you out. Okay. Why do the glycosidic bonds in maltose and lactose only contain either an alpha or a beta instead of both? So why did we do that? Anybody any ideas? Oh, only one glycosidic bond, right? So only one anomeric carbon participates in a glycosidic bond. Right? Only one. That's exactly right. Okay, so now the next one, now that you are so sure you know, name and locate the glycosidic bond in the following disaccharides. So take a second and identify where is the glycosidic bond, and then we'll name it together. So you should be looking for an anomeric carbon. Ooh. You're looking for an anomeric carbon, and that anomeric carbon, where it is attached to the oxygen, that's my glycosidic bond. If I do it in the next one, right, where's my glycosidic bond? I find my anomeric carbon and where it's attached to the oxygen. Because this one right here is not an anomeric carbon. So it's not going to be the glycosidic bond. So now take a second and identify A. How would you name the glycosidic bond in A? Okay, it is beta 1,4. So it's beta 1,4 because beta is top, and top, that's my son's initials, CB. That's how I remember, right? so cis and beta go together. All right, and then we know that it's a 1,4 because it's 1, 2, 3, 4, 5, 6, right? So that's where our 1 comes from, and then we go 1, because that's our anomeric, 2, 3, 4. So it's a 1,4. Okay, how about B? What do you get for B? This one is alpha 1,6. Y'all are rocking this today. This is awesome. Okay, so how do we know alpha? Well, we see this is top and this is bottom, so that gives us the alpha. Then our numbering, this is anomeric, so we go 1, 2, 3, 4, 5, 6, and then we go, here's our anomeric, 1, 2, 3, 4, 5, 6. So alpha 1,6. And it is trans, which means alpha. Yep. Yep. Okay. And 8, y'all were supposed to be in groups, but it's fine. We got to roll with it today. All right. So the next one is to identify a reaction. Is this a condensation reaction or a hydrolysis reaction? Let's answer that first. Take a look and think about it. So we are adding water. We are not producing water. In this case, we are adding water, not producing water. So it has to be hydrolysis. If it were condensation, I would have to make a product that was water. But I don't. I'm actually going to use water in this reaction. So if I'm going to use the water, I'm going to break it, and it's going to be hydrolysis. Okay. Could you scroll up this one? Good, Carolyn? All right, so if we're going to undergo hydrolysis, remember our general reaction, right? We have something that has an oxygen between it. We add water, and we're going to make two products. One product, each of the products is going to have a hydroxyl. Oh, I did that backwards. HOR, and we're going to produce. So we go from having one original big molecule to now having two smaller molecules. And how did we do that? We did that by breaking our water. So if we have our water, water is really HOH, right? So we're going to split our molecule. And we're going to take one of these hydrogens, and we're going to give that hydrogen to whichever molecule gets the oxygen. So let me do that a little bit better, right? It's going to go on that oxygen. Now the OH is going to go on the molecule that didn't get the oxygen. So how do we do that? Well, let's look at our, this is going to be our product. I'm just going to erase what was there. I'm going to try. Okay. So on that first molecule, I'm going to put a line down, and I kept my oxygen, and then I got a hydrogen from water. On the next molecule, I didn't keep the water at all. I didn't keep the oxygen at all. And so I need to put both the oxygen and the hydrogen that was from water. So this is that one, and this is that one. The worksheet does not have the second reactant. No, I just copied and pasted. It didn't have any of the, what do you mean it didn't have the second reactant? I made this. I did this. You'll have to draw this. Okay. Yeah. So, but all I did was I took the original molecule, I copied and pasted it, and just got rid of this interaction right here, and gave oxygen to one, put a hydrogen from the water, and then on the other one that didn't get an oxygen, it got the hydroxyl. Okay. All right. Okay. And what do we have to do anything else? And provide the products. Okay. Anybody, if this is D-maltose, what are our two products? Anybody know? This is one of those you could put on the flashcard. What kind of products are you making? Two D-glucose. Glucose plus glucose, that's right. That's right. Good. Y'all got this. All right, B. B, what kind of a reaction are we doing? Ah, now we're doing a condensation. This is a condensation. Okay, so remember, in condensation, water is going to be one of our products. So where did that water come from? The water is going to come from, one group's going to give a hydroxyl, and the other group is going to give a hydrogen. That's where it's going to come from. So what I'm going to do is I'm going to copy what I originally had, and you can just draw, but I'm going to take my individual monomers, and I'm going to stick them right there. And I'm going to copy this one. Let's stick him right there. Don't want to scoot over. See? No, it just doesn't want to go over. Okay, we'll try that. All right. So I'm going to erase the water. We'll put it down here. We'll say you're going to produce water. Okay. So how do I make this new product? Remember, this is going to be my R attached to an OH plus R attached to an OH, and I'm going to form ROR plus water. So I'm going to have my individual sugar rings, and then in between those sugar rings, I'm going to have an oxygen. So how does that work? Well, I need to take away the hydrogen from one of my molecules, right? And then from the other one, I'm going to take both the oxygen and the hydrogen. So how does that work? Then you just make that bond, and that's it. Okay? So that's the formation of our glycosidic bond. Well, it's actually the other way around. Honestly, watch. Honestly, it's really, this one's going to lose the hydroxyl, this one's going to lose the hydrogen. But it doesn't really matter. It doesn't really matter that you know which one is which, so long as you can make the product, right? So this one kept the oxygen, and it's the one that's going to make the new bond with that anomeric carbon. But it doesn't really matter. So y'all okay on that? Yeah? Okay. All right, circle the glycosidic bond. This one's an easy one. So you got to find that anomeric carbon and look at where it is bound to that oxygen that's outside of the ring. So it would be right there, because there's my anomeric carbon. It's a little trickier on the next one. On B, can you find the glycosidic bond on B? Find that anomeric carbon and then see where it's attached to the oxygen outside of the ring. And that's your glycosidic bond. So it could be attached to anything. It doesn't have to be a sugar. Could be anything. All right. Now we have a trisaccharide. So you have 3 monomers, A, B, and C. Name the glycosidic bond between monosaccharide A and monosaccharide B. So try and name that bond. Give people a few minutes. Well, not a few minutes, but you know, a minute. I'm going to say, does anyone have a different answer? Alpha 1,3, Alpha 1,3. How did you get Alpha 1,3? Let's take a look. All right, so on our first carbon, here's our anomeric. We have nothing attached to it, so we count it as 1. Here's our anomeric carbon. What do we have attached to it? A C2OH. So this carbon becomes carbon number 1. My anomeric becomes carbon number 2. So this one is carbon number 3. So the carbons participating are carbon 1 and carbon 3. This is where y'all weren't counting that first carbon. But the point of doing this is that so you make that mistake here and not on the exam. I know it looks confusing. It looks kind of scrunched because they put in all the hydrogens and they put in the numbers. They just put in a lot on there. So I'm going to try to make sure that our structures on our exam are a little neater. But okay, so we have our carbon 1 and carbon 3. And then how did you know it was alpha? Well, the anomeric carbon that's participating, we find its carbon that's on the outside of the ring, and we look at the glycosidic bond right here, and they are opposite, they're trans, and so trans is telling us that it's alpha. That is correct. Okay, label glucose and fructose. Do you know which one is which? Glucose and fructose. You don't actually have to be able to recognize these based on structure. This is not something I would ask on an exam. It's not. but can you recognize it? So glucose, tell me which monomer, A, B, or C, is glucose? A. Any other ones? It's actually A and C. Good. A and C. So fructose is our B. Glucose is that 5 carbon, but in the ring of 6. And then our fructose is only 4 carbons in the ring. So that's how you can tell. All right. So now we want to go on to this one. No, not this one. We did that one. This one, reducing sugars. So this is something I think the book didn't do such a red hot job on. And so I thought y'all could use a little bit of reinforcement on this. So when we talk about reducing sugars, you have to remember your oxidation reduction trick. So remember when I was telling you things that you could write on your scratch paper? This would be one of them. So if you're oxidizing, how do you know you're oxidizing? If it's oxidation, what do we remember? So oxidizing is gain in oxygen. And then you could also, nobody else said it, but you could lose a hydrogen. And then you're remembering oil rig, right? So oxidation is loss of electrons. Okay, so how about reducing? In reducing is gain of electrons, and then you gain hydrogen, and I'll put a line there, or you can lose oxygen. Good. This is something I would definitely write down before you start trying to answer questions on the exam. Absolutely. Okay, we got that? All right, so we're gonna move on. All right, so a lot of times we need to know if we have a reducing sugar in solution, and so we do this Benedict's test in order to determine that. So in a Benedict's test, if you have a reducing sugar present, the Benedict's reagent will change color from blue to brick red. So that's how we can visually see what happens. So my question is, if you have D-glucose here and it turns into D-glucagonic acid, is this an oxidation or is this a reduction? So take a look at just that structure and tell me what you think it is, oxidation or reduction. We have oxidation, but it's because you are gaining oxygen. What oxygen did you gain? Right here. Everything else in the structure is exactly the same, except on our original structure, we had a hydrogen, and our new structure, we have an alcohol here. Okay, now I'm going to give you a little bit of a trickier question. The copper 2 ion, when it goes from the copper 2 ion to our product, is it undergoing oxidation or reduction? This one is reduction. How do you know it's undergoing reduction? Well, it started out as Cu2+, and it turned into Cu2O. So it started out as a +2. What's the charge on copper here? You have to remember how we write a formula for copper and for oxygen, right? If I want to know that, I have to go to the periodic table and I have to go and see what column is oxygen in. I would see it's in 6A. And so it would want to gain 2 electrons. And so it would be a -2, right? So when we'd write the formula, we crisscross whatever charges were there. So that would become a 2. And I know from the formula over here that this is a 1. So what originally had to be up here in this empty space right here? Not a +4, a +1, a +1. So it's just like kind of reverse crisscrossing. So if we went from a +2 to a +1, what happened? Did we gain electrons or lose electrons? We gained 1 electron, because if you're a +2, we need to add 1 negatively charged particle to get a +1. So you have to have gained an electron, and a gain of electrons is reduction. Okay? Y'all with me? We're almost done. Okay, so how can we look at these sugars and know if these sugars are reducing or non-reducing sugars? All you look for, right, are carbohydrates that have free anomeric carbons. So that is an anomeric carbon that is not in a glycosidic bond. These are reducing sugars. So tell me in A, alpha D glucose, reducing or non-reducing? This one is reducing. Why? Here's our anomeric carbon. Ooh. Here's our anomeric carbon. Is it participating in a glycosidic bond? There's no glycosidic bond, so no, right? How about beta D fructose? Is it reducing or non-reducing? It's reducing. Because here's our anomeric carbon. Is our anomeric carbon participating in a glycosidic bond? There isn't one. So the answer is no, it's reducing. How about here? Reducing or non-reducing? Now be careful with this one. You have an anomeric carbon here, and you have an anomeric carbon here. So C1 here is non-reducing. But this carbon, this C1, is reducing. So what would happen is if you had this in solution, you would end up getting a positive result. So D-lactose as a molecule is reducing because it has a free end. Now, if you had a chain that was a polysaccharide that was 10,000 glucose units long, we would call that non-reducing because you have so few ends. But if you have a disaccharide, that means every other one is going to have a reducing end. And so you would call it reducing. How about D-sucrose, reducing or non-reducing? So this one is non-reducing. Here's our anomeric carbon. Here's our anomeric carbon. What do you notice? They're both non-reducing. So overall, as a molecule, D-sucrose is non-reducing. Right? They're connected by the glycosidic bonds between 2 anomeric carbons. So what could you tell me about all monosaccharides? are reducing because they have no glycosidic bond. So they're all reducing. Now, disaccharides can go either or. Oligosaccharides can go either or. Polysaccharides are all non-reducing. Okay. All right. And so we really answered number 4. Right. All right. I think I'm supposed to end at 2:50. So I'm going to call it. I think we have one more question, but this is as far as we got in the other class too. So it's A-okay. Y'all have any questions?
Hope says hey.
I hope.
Almost the whole class, but we didn't make it to the end.
Well, at least you didn't have to tell her that you were going to go in her room and throw away her toys. We're not there yet, right? So cute. She was so good for all class.
All right. Bye, Dr. B.
Bye. Y'all have a great weekend. Y'all stay safe, and let me know if y'all need anything. Thank you. All right, I'm going to go ahead and end the Zoom. If y'all have any questions, just let me know. Just send me a quick email.